right, so continuation of worksheet number 4, problem number 5. All right, let's see what we got here. We have this chemical reaction where we're combining ammonia with copper 2 oxide, and we get 3 products out of the deal. So in the problem, it says that we've got 57 grams of ammonia, okay, and that's going to combine with 290 grams of copper 2 oxide. All right, so when, if I'm just trying to connect this to previous problems, when we do like a simple mass to mass problem, I would only give you the mass of one of these reactants, and we would assume that we have an excess amount of the other, and then I would ask you, hey, how much nitrogen could we make, or how much elemental copper could be made. But here you've been given the amount of both ammonia and copper oxide, and we cannot assume that we have exactly a 2 to 3 mole ratio between those two things. Okay, we cannot assume that. One of these is probably going to run out first when we do the reaction with those two amounts of compounds. So to identify the limiting reagent, the first step is to convert these masses to moles. 57 grams of ammonia is, let me put moles down here. Okay, moles. That is 3.35 moles. And 290 grams of copper 2 oxide turns out to be 3.65 moles. Okay, now if in order to determine which one's limiting, and this is probably this is the trickiest part, since this is kind of the new facet of working stoichiometry problems. If you have 3.35 moles of ammonia, okay, then you're going to need more than that number of moles of copper 2 oxide, right? Because there's a 2 to 3 ratio. And when two things are combining in a 2 to 3 ratio, what that means is for every one of this thing that's required, you need 1.5 times that much of the other thing. So you have to ask yourself, do I have 1.5 times this amount of the copper oxide? Well, I think you can see when you compare these two numbers with each other, 3.35 and 3.65, that you certainly, 3.65 is not 1.5 times bigger than this number. Okay, so from inspection you can see that the copper 2 oxide is the limiting reagent. Okay, so whoops, copper 2 oxide, that is the limiting reagent. Okay, now if you wanted to figure this out a little bit more formally, you could say, well, let's see, the number of moles of copper 2 oxide that we need is equal to 3.35 moles of ammonia times the mole ratio between those two things. And so 3 moles copper 2 oxide, 2 moles of ammonia. Alright, and so this way the moles of ammonia cancel. When you multiply 3.35 times 1.5, you get 5.02, something like that. And we certainly do not have that much. Okay, so this is another technique. This is probably closer to the strategy your book recommends. And that's another way to determine that the copper 2 oxide is the one that's limiting. Okay, and so once you know that, then you just set up your, if you want to figure out what's the mass of nitrogen gas that could be made from these two amounts of starting reactants, then you would just say, mass of nitrogen equals we're going to use the amount of material from the limiting reagent, so that's 3.65 moles of copper 2 oxide. Now I'm not going to do the mass to moles conversion because it's already in moles, right? So now we're ready for the mole to mole ratio. Okay, and for this, the two mole numbers that we're connecting here are moles of copper 2 oxide, that's our limiting reagent, okay, that's this, to the moles of nitrogen. Okay, so there's 1 mole for the nitrogen and 3 moles for the copper 2 oxide. All right, because it takes 3 moles of copper oxide to form 1 mole of nitrogen, and then we do have to convert that number of moles of nitrogen to the mass of nitrogen. Okay, so that's the setup, and when you do the arithmetic, you get 34.0 grams of nitrogen. Okay? Okay, excuse me, let me just make sure I keep track of the time. All right, now let's go to the next problem. Number 7. Number 7. This one, I believe we worked in class today, but just in case, all right, so this one is a simple mass to mass conversion. So you're being told that we have 4.0 grams of hydrogen, right? Here it is in the problem. And you have an excess of carbon monoxide, so you don't have to worry about running out of the carbon monoxide. This is going to be your limiting reactant in this case, and you're being asked to determine how many grams of the methanol can you make. Okay, so easy. Mass of methanol equals 4.0 grams of hydrogen times 1 mole over hydrogen over 4.0, I'm sorry, whoops, I'm looking at the 4. The molar mass of H2 is 2 grams. All right, so that's the mass to moles conversion for hydrogen. Now, we are connecting these two, hydrogen with methanol, so that's 1 mole of methanol over 2 moles of hydrogen. Okay, and this is the only conversion factor, just a reminder, the only conversion factor where you have to take the coefficients from the balanced chemical equation. That's where we use them. And then finally, we need to convert moles of methanol to mass, and so for that we need the molar mass of methanol, which is 32 grams. Okay, and when you crank all that out, you will get 32.0 grams of methanol. There we go. Okay, now then you are okay, let me back up. What we have calculated here is what's known as the theoretical yield. So theoretical yield. In theory, if you're given 4 grams of hydrogen and an unlimited supply of carbon monoxide, you should be able to make 32 grams of methanol. Okay, but for reasons that we discussed in class, the amount that you will actually be able to make in lab is it's always going to be less than the theoretical amount. So let's say, for example, that when you do this in lab, experimentally you are able to make 28 grams. And the question is, what would be the percent yield? Okay, so that's equal to the actual yield, actual yield divided by the theoretical yield, that fraction multiplied by 100, which in this case is 28.0 divided by 32.0 times 100, and that equals 87.5%. That is the percent yield. Easy, no problem. Okay, all right, let's go on to number 9. I'm going to go a little bit faster here. Let's see, how many grams of potassium chlorate are needed to produce 5 liters of oxygen in STP? All right, for this, I'm going to assume that you should be able to do this calculation. This is something that we cover on worksheet number 3. So I'm just going to say here that the answer is 18.2 grams of potassium chlorate. Okay, and then down here, okay, it's a little bit of a funny problem because this is kind of just a review problem, but you've been told that you've produced, or that you should be able to produce 5 liters of oxygen. Okay, so the theoretical yield of oxygen is 5.0 liters, okay, at STP conditions. Then down here it says, well, suppose that the reaction described above produces 4.80 liters, okay. What then would the percent yield be? All right, well, I think you know from above, percent yield is equal to the actual, which in this case is 4.80 liters, divided by the theoretical, which is 5.0, times 100, and you should get 96%. All right, and then finally, let's see here, number 11. Okay, if 50.8 grams of calcium carbonate decompose to produce 26.4 grams of calcium oxide, okay, so that's 26.4 grams of this stuff. What is the percent yield of calcium oxide? Well, let's take a look here. Let me label the amount we've been given here. So that was 50.8 grams. All right. Well, they're telling you how much calcium carbonate they're giving us, and then they tell you that it's decomposed and you've obtained 26.4 grams. Okay, and then they're saying what is the percent yield? Well, that is kind of, when it asks what's the percent yield, that's kind of a giveaway that the theoretical yield of calcium oxide is probably something higher than 26.4 grams. So what we need to do is a mass to mass calculation to find the theoretical yield. This, what we've been given, is an actual yield. Okay, all right, so quickly, if we set this up, mass of calcium oxide equals 50.8 grams of calcium carbonate. That's the known, and you're going to go through and do the usual 3 conversion factors, and when you do that, you should get an answer of 28.5 grams of calcium oxide. Okay, that is the theoretical yield, and so then the percent yield is then equal to the actual yield, all right, which is 26.4 grams, divided by the theoretical, 28.5, all times 100, and you should get 92.6%. Okay, so part of the challenge here was sort of the interpreting that this is an actual yield. Okay, thank you very much. We'll see you tomorrow.